that I am honored to be to speak at this conference and to see all of you. It feels like a continuation of the celebrations we had in Oslo back in May. So I was also privileged to be part of that meeting and that celebration of Robert Langlands receiving the Abel Prize. And when I also had a chance, opportunity, privilege to give a public lecture, and I remember I said, the Langlands program now has become such a vast subject, and we are all one big family now, and we work in different fields, some in number theory, some in harmonic analysis, some in geometry, some maybe in physics even, and but we are all a family, and I think it's really something. As I was speaking it, I was myself surprised that I was moved by it myself. I was like, what I mean, like, wow, it is true. And look at you, look at you. It's a family gathering. That's what it is. It's like a Thanksgiving, So you have, grandmas and grandpas and unruly youngsters and an eccentric uncle, So, yeah. So, and the older I get, the more I appreciate that human element and human connection, and we should never forget that behind those beautiful theorems and equations that we discuss, there is also that human connection. That's something that we all share. That's something we are all passionate about. All right. So I was asked, as Bill said, I was asked to speak about Robert's paper, which he posted online of the Institute, on the website of the Institute for Advanced Study back in April, and shared amongst a few colleagues, but it has been available, publicly available since April. Not as available, I suppose, as most papers that we are used to, because they are usually written in English, and this paper is written in Russian. And, that's another thing which I have to say. As the older I get, the more I appreciate that. What he's doing in that regard, Langlands is doing in that regard, is that our treating English as a kind of a common denominator, but without using and unfolding the true beauty of the language, but just using it as a transactional sort of way of communication, is depriving us of some very important strata, very important dimensions of our culture. And so I feel as though, Langlands has been on a crusade of sort of reminding us about the importance of those dimensions. And so that I think there is something to learn from that fact that, as Bill has mentioned in his introduction, the only two available sources for that work at the moment are in Russian and in Turkish. So, which in a sense, it's nice because it means that young mathematicians in Russia or in Turkey sort of have a head start, right? So, anyway, so I feel privileged that I, by virtue of historical accident, one might say, actually speak Russian happens to be my native language, and so I was asked, for that reason in particular, to speak about this work at this meeting. And I am grateful. Actually, I'm grateful that to the organizers for doing that. Even though many a time I was in my, in front at my desk saying, "Oh my God, why did I get myself into this?" So, why did I say yes? Well, I grew up in Russia, so we have respect for authority. So it's anyway. So I actually wrote notes, which I never do this. It's really something new for me. I wrote notes for this lecture, and they are available on a web page. I should have written them in Turkish, but as a way of learning the language, you know. But actually, I wrote in English. Okay, so I wrote them in English. It's a UC Berkeley website. Can you guys hear this? Is that? Analytic PDF. I think it should work. At least I tried this morning and it works. Okay, so obviously I only have 1 hour and actually much less than that now after all this, after this beginning. So whatever I will not manage to say, the details can be found in this manuscript, in these notes, and of course I'll be happy to also discuss afterwards, etc. It's a fascinating subject, as you will see. As I hope my main goal is to perhaps say that there is some interesting questions here that are definitely worth studying. Let me first set up the context, talk about the context of the where this work is coming from. So the Langlands program, one of the ways to talk about the Langlands program is to think of it in terms of André Wei's Rosetta Stone. So the famous letter by André Weil, which he wrote from jail, to his sister Simone Weil in 1940, in which he emphasized analogies between 3 different realms, 3 different domains. Now, those analogies were known to other mathematicians before, and André Weil acknowledges that. However, his presentation was perhaps the most eloquent, and has remained, in my opinion, one of the most eloquent in emphasizing those analogies. So the 3 realms are number fields, function fields. So in the traditional approach, in the original work of Langlands about 50 years ago, those were the 2 realms. Function field referred to the field of functions, of rational functions, on a curve, on an algebraic curve defined over a finite field. That was the function field at that time. However, there is a 3rd domain which was not within the scope of the original program, the way it was presented in the Langlands in his letter to Weil, actually, 1967, and his subsequent paper in the Springer lecture notes, 1970, etc., but which has become very much part of the Langlands program in the last maybe 30 years. And that's the case of function fields for curves over the complex field. So I would just write curves over C. Complex curves or Riemann surfaces. And so those 2, as I already mentioned, are within the scope of the, let me say, traditional or original Langlands program. Original formulation of the Langlands program. However, the formulation for complex numbers is different. And that formulation has an analog for function fields for curves over finite fields as well. So these 2 realms, so to speak, these 2 columns, these 2 languages of the Rosetta Stone are combined today into what's known as a geometric Langlands program. And so what is this all about? Well, to explain how this came about, I need to say a few words about what the Langlands but one aspect, well, obviously Langlands program has different aspects as well. There is functoriality. Two of the major aspects are functoriality and correspondence, the Langlands correspondence. What I'm going to talk about today is mostly about the Langlands correspondence. Obviously, it's not the whole thing, it's part of the project. So to set it up, let me say something in this domain. It's kind of a sweet spot where everything kind of intersects. And there is one case which is relatively easy to explain, which is, so let me take f to be the field of rational functions on a curve. So maybe rational functions, and I will call it this fq of x. So that's the one I'm talking about. It's a function field where x is a smooth projective geometrically reducible curve over a finite field of q elements, fq. So then we have, for this f, we have the ring of Adels. And then inside the ring of Adels, we have the ring of integer OF. And so let's suppose that we would like to study automorphic representations of the group GLN. GLN of A. So representations of the group GLN of A that we want to study are the automorphic representations, which roughly speaking can be realized in functions in some sort of functions on the quotient of G of F, of G of A divided by G of GLN in this case. Let's say GLN. Okay, so now F is also naturally here. And so the group actually acts from the right, so maybe it's better to write it like this, GLN AF. And so the question is to classify the irreducible representations which appear under the decomposition of the space. Now, there's some technical issues with central character, etc., because the space is not compact, but let's ignore that for the moment, or let's just say we fix a central character. So the Langlands correspondence in this case, is actually a theorem which is due to Drinfeld for n equal 2 and Laurent-Lafourgue for n greater than 2. It sets up a one-to-one correspondence between irreducible representations which appear here, so irreducible. Actually, I like to write it in this way. On this side, irreducible automorphic representations of GLN of A of F. Now, to make it a little bit neater, I will say that they have a finite central character of finite order, and also I will take Caspillo representation, but I'm not going to write it down just to save time. And these are in one-to-one correspondence with equivalence classes of representations, n-dimensional irreducible representations of the Galois group of F bar over F bar being the separable closure of F, and we take irreducible representations with some condition on the restriction to the center to match the finiteness condition for the central character to make it a little bit nicer. Also, these have to be analytic representations, so they land in a GLN over finite extension of QL, the field of analytic numbers, where L is different from the characteristic of FQ. So there are certain issues that need to be addressed, but roughly speaking, that's what the Langlands correspondence is. Irreducible automorphic representations arising in the space, and the functions on this quotient are parameterized by irreducible n-dimensional representations. Maybe I will write cuspidal because it is an important condition to get this irreducible. Okay, so now there is a way to shrink the size of this. These are infinite dimensional representations, but they have finite dimensional space of invariance under various compact subgroups of this GLN. And in fact, by using such a compact subgroup, we can then pass to a more manageable, so to speak, double quotient. We lose the action of the group on the right, but instead we have an action of a certain Hecke algebra, namely the Hecke algebra of k bi-invariant compactly supported functions. And the nicest, so to speak, the first case to consider here is the case of a maximal compact subgroup. And the maximal compact subgroup is GLN of O. And so we end up with a double quotient of GLN of A of F by GLN of F by GLN of OF. This is a maximal compact. And then we can take some space of function. For instance, we could just take L2 functions here with respect to a standard measure. The algebra which acts here is called the spherical Hecke algebra. It is actually a restricted tensor product of local algebras labeled by the closed points of X. And each algebra, Hx, is isomorphic to the representation ring of GLN. This is called the Satake isomorphism. So these operators then, elements of this algebra corresponding to representations of GLN, act on this space. They commute with each other. So we get commutative algebra. And the operators are called the Hecke operators, or unramified Hecke operators of, and maybe I will use here another color, Hecke operators. So Hecke operators are very important in the story because they are the ones which represent what remains of the action of the group on the single quotient when we take a double quotient. And therefore, their eigenvalues and eigenfunctions on the space are very meaningful. They are the signatures, they are the traces, so to speak, or they are the objects which encode automorphic representations. Not all, but the ones which have a vector invariant under the maximal compact subgroup. Indeed, if there is a representation which occurs in a single quotient and it has a vector which is invariant under k, then that vector gives rise to a function of a double quotient. If k is a maximal compact subgroup, we get a function on this specific double quotient. That function will necessarily be an eigenfunction of the Hecke operators. So that's why the question of finding, let's call it spectral analysis. It leads us to the question, to the spectral analysis of these algebras, Hx, or X belongs. Now, I have chosen the group GLN for the simple reason that, first of all, in this case, the Langlands correspondence is a theorem, whereas in other cases, even though we have many partial results, it's not really. Well, I guess for classical groups, I suppose we have it as a theorem now. But also there are various issues which arise, subtleties which arise for other groups. But roughly speaking, what would happen for a general group is that we will replace this double quotient by this. And then the Hecke algebra, again, will be a tensor product over points, but each local factor will be isomorphic to the representation, complexified representation ring of, not of G, but of, obviously, as we all know, of another algebraic group over C, in this case, This is going to be C algebra, which is the Langlands dual group. And that's how the Langlands dual group makes an appearance. And so then the point is that if we were to take G of A of F, then the Langlands parameters, even though the story is way more complicated than for GLN, but an essential ingredient in the story is a homomorphism with values in algebra. Ah, okay. So now I know which to use if I don't want you to see what I wrote. Thank you for this. So neither blue nor red. All right, sir. We'll stick to black. Black and white. So, all right. Now let's see what happens, what we can possibly, having this in mind, how could we possibly generalize this story to the case when X is a curve not over a finite field, but over the complex field. So in this case, we have to take the double quotient again, right? So X is a curve over C. And so we can define the same objects in a similar way. In particular, we now have F, which is C of X, the field of rational functions. Then we have the ring of ideals, the restricted product of the completions corresponding to closed points. And inside we have O of F. Maybe I should say this is an ramified case. So let's just stick to the unramified case. So we take the double quotient of G, let's say G of A. G is a reductive algebraic group, connected reductive algebraic group over C. And we have this double quotient. And so the first observation, which has informed this sort of passage from the curves over finite field to the complex field, is something which is already valid for the finite field, and that goes back to André Weil, is a statement that this double quotient actually is, as a set, is in bijection, in one-to-one correspondence with isomorphism classes of principal G bundles on X. This is true for both over FQ and over C. But at least for split, and let's say split for FQ, maybe have to be a group which is split already over finite field. And so there is a tantalizing possibility opens up, which is that we realize that actually this is a set of points, or it could be a set of points of an algebraic variety over C or over FQ, depending on whether our curve is over C or over FQ. Namely, the moduli space of G bundles on X. Now, it turns out that this doesn't quite work in the abelian. It works in the abelian case. If G is GL1, or in general a split torus, let's say, then indeed, this set is a set of points of an algebraic variety, and that variety is a Picard variety for the group GL1. Moduli space of GL1 bundles, which is the same as the moduli space of line bundles. And that is what's called moduli problem, which has a fine moduli space. But for non-abelian groups, because of the complications with automorphisms of different bundles, it's relatively easy to see that there is no such algebraic variety which would encompass all principal G bundles on X. But instead, we have sort of the next best thing, which is called algebraic stack. Algebraic stack. And it is called, the notation for it is bund G. Bund for bundles. So actually, there exists an algebraic stack called bund G such that the set of its points, its closed points, or isomorphism classes, because these points are groupoids. Right? It associates to points is not sets, but groupoids. Isomorphism classes are precisely isomorphism classes of principal G bundles. And so we see how the situation becomes very different, because you see, so over FQ, you have the Picard variety. So let's say GL1. G is GL1. We have the Picard variety of X, which is now defined over FQ. And then we have the set of points of this Picard variety. And we consider functions on it. So that will be that very concretely the space of this double quotient, which appears here, which is the subject of abelian class field theory. And in fact, many of the results, familiar results from abelian class field theory, can be cast in terms of line bundles rather than adels. And sort of there's a nice, very satisfying geometric picture describing the abelian class field theory in these terms. But now, look, so it makes sense to take functions on this, on the FQ points. So functions on this, or L2 functions, makes sense. For one thing, it is really it is a union of components labeled by the degree of the bundle, and for the number of FQ points is finite for each of these components. So it's a nice sort of disjoint union of finite sets. But in fact, the whole action is happening on one of the components. So it's really got functions on finite sets. So it's a really nice theory. It's a rather simple theory. You have a finite dimensional vector space and some specific operators acting on it. And so you just diagonalize them. So that it is. It's a very simple exercise in function analysis. But if you look over the complex field, look, now you get a Picard variety, and you take C points, you get a torus. So you get something like, for a curve defined, for a curve of genus G, you're going to get something which is isomorphic to 2G plus 2G dimensional torus. Now, what kind of functions should we take? You see, so I think that what happened when people looked at it in the 80s, it was mostly algebraic geometers who looked at this question. And for algebraic geometers, it's natural to look at algebraic functions, which for a compact variety means holomorphic functions. So then we know that, well, maybe isomorphism is peak zero. We know that they're only constant functions. So you don't get anything algebraically in this way. And that prompted people to look for other ideas, look for other possibilities. So what did people come up with? So the idea was to go back to the intermediate case. Remember, we have the Rosetta stone, where you have number fields, function fields for curves over finite field, and function fields for curves over C. And now, if we work with a curve over a finite field, there is a refinement of the theory of automorphic functions. So now we have automorphic functions, or automorphic forms, if you will. I will use the term functions to emphasize that we are dealing with functions rather than sheaves, which are coming up in a minute. Automorphic functions for GL1 unramified. Are functions on the Picard variety. of X. The set of its FQ points, right? And on this space, on the space of functions on it, well, we can take some unspecified space of functions at the moment. It doesn't matter. We have the action of these Hecke algebras, which in this case is just each algebra is just isomorphic to polynomials in one variable. Well, Laurent polynomials in one variable. So we are talking about eigenfunctions. The automorphic functions are eigenfunctions of these commuting operators. Let's say f with some label lambda. Now, we learned from Grothendieck that that oftentimes interesting functions coming from representation theory is in particular on FQ points of an algebraic variety over FQ. And this is an algebraic variety over FQ, and we are taking FQ points. That's the meaning of the double quotient, which I have erased in this case for the GL1. So Grothendieck has taught us that oftentimes these functions come by what he called the sheaves to functions dictionary. That there is a procedure which enables one for varieties over a finite field to produce functions out of what's called analytic sheaves. And this is very important. It has been one of the, well, Grothendieck obviously had many good ideas, but this was one of the major ones, which has influenced tremendously development of mathematics in the last 50 years, I would say, if not more. So Grothendieck's idea was that if there is an analytic sheaf, it doesn't matter at the moment what it means. Just think of something like a local system, like locally constant sheaf in the étale topology in this case. But one can have a model if one is more familiar with other settings. That's fine too. And the analytic sheaf on a variety, let's call it Z over a finite field, then we can attach to it a function f with the index f, so I keep track of this of the sheaf from the set of FQ points to Q bar. And it is constructed as follows. I choose a point x, which we take a point x in Z of FQ. Actually, we could take any closed point, but to make the point that I want to make, it's enough to take FQ points. You take this point, so you have the stalk of this, of the sheaf, f, at this point. But now, x, you can think of x as a map from spec of FQ to Z, and you can pull it back. FQ is not algebraically closed. We can pull it back to spec of x cube FQ bar, and we know that the Galois group of FQ bar over FQ is topologically generated by a specific generator, the Frobenius. What it means is that if you have an analytic sheaf on spec of FQ, it gives you not only a vector space, which we would get if we were dealing with just an algebraically it's the only thing we would get if FQ were algebraically closed. But we are getting it with an automorphism, with a Frobenius. And so we can take the trace. Actually, we get not an automorphism, but a conjugacy class, but we can take its trace. So we get a number. And more generally, we take not just the trace of the Frobenius of x. It's not a good notation. I should probably call it x bar. So this is x, and this is x bar on fx bar. In general, you take the alternating sum of the trace of the Frobenius on the Stokes cohomology. So that's a construction of Grothendieck. So you can go from sheaves to functions. And moreover, this construction behaves nicely with respect to natural operations on sheaves. If you have an exact triangle of sheaves, then the function corresponding to the middle one is the sum of the functions corresponding to the two appearing on the sides of the exact sequence. If you have a tensor product of sheaves, you get the product of the functions. If you have a pullback of a sheaf, you get the pullback of a function. And the best part is if you have a push forward with compact support, direct image with compact support, it corresponds to the integral of the function. So it's really nice. And in fact, these days, we think of this as a kind of idea of categorification. We have placed this idea of Grothendieck, or in fact, it has inspired mathematicians to consider this idea of replacing objects of sets or replacing elements of sets by objects of categories, replacing sets by categories, replacing elements by objects, etc. This is often referred to as categorification. And it is a really powerful thing because, and I hope I'll have time to explain one of the reasons for that. But anyway, this has been around for a long time. And so now, let's combine these two ideas. So we say automorphic functions for GL1 are functions on the FQ, on the set of FQ points of an algebraic variety. So this is going to be our Z, right? This is going to be our Z now. Like here. We have a function on the FQ points. Is there a sheaf? Is there an analytic sheaf on the Picard variety which would give rise to these functions by the Grothendieck dictionary? And the answer is yes. And in fact, that sheaf was constructed by Pierre Deligne, I guess late 70s or early 80s. And this was really the first result of geometric, or what we now call the geometric Langlands program. So instead of a function, automorphic function, which is an eigenfunction of the Hecke operators, maybe I should have written this, since it's very important, Hecke operators. So these functions actually have sort of something above them. We can promote them to sheaves. And those sheaves are, in fact, have a special property, which is analogous to the Hecke eigenfunction property of the corresponding functions. These sheaves are what are called Hecke eigen-sheaves. So, in fact, automorphic Hecke eigenfunctions come by the Grothendieck dictionary from Hecke eigen-sheaves. Eigenfunctions on the set of points of the Picard, of FQ points of the Picard, come from Hecke eigen-sheaves. Now, what is that about, Hecke eigen-sheaves? So we understand sheaves more or less. What is a Hecke eigen-sheaf? Well, what is an eigenfunction? An eigenfunction is something that if you multiply it by certain operators, you get back the same function times a number. Now, when we categorify, numbers get replaced by vector spaces. In fact, that's how we got the values of this function in the first place. They came from the vector spaces, namely the stalks of the sheaf. And we take the trace of the Frobenius, right? And so Hecke eigensheaf means, whereas here you have Hecke operators, hx, and the function you get multiplied by lambda x. Here you have a Hecke functor, which I'll write with a curly h, and you have a sheaf f, and when you apply it, you get back f. It's isomorphic to f itself. But see, there is a very interesting thing. So you say, well, if it's isomorphic, where are the Langlands parameters? Because here, the parameters are these numbers, lambda x, where x is a closed point of the curve. And to relate them to the Langlands parameters, which are the unramified one-dimensional representations of the Galois group, but my precise actually here is Weil group, we interpret them, we say that there exists a one-dimensional representation, unramified representation of the Weil group, such that these numbers are the images of the Frobenius for each x. In general, you have Frobenius conjugacy classes, but this is a abelian case, so we can just say images of the Frobenius. And that's how, in the classical, so to speak, function theoretic setup, we are relating automorphic functions, Hecke eigenfunctions, more specifically on the Picard, on the points of the Picard, FQ points of the Picard, to to Galois representations. But here we do it differently. And the way we do it is we say that actually this isomorphism depends on the point. So in fact, we could say that this isomorphism is a tensor product with a one-dimensional space. But in fact, let's write this one-dimensional space as Ex. So this is one-dimensional. So as a space, it doesn't depend on X, but the isomorphism depends on X. And as we move the point around, suddenly the local system appears. You don't need any Frobenius classes anymore. You don't need any numbers attached to points. And then so there's always this issue. When I was learning the subject, many years ago, I was always, how can I get the actual local system and not just a collection of conjugacy classes? Now, by Chebotarev theorem, for instance, we know that there is at most one Galois representation given a collection of Frobenius conjugacy classes, right? But where is it? It's like, how do you construct? Well, guess what? In the geometric theory, it shows up by itself as a kind of as a bonus. You don't have to pay extra for it. It comes out of this isomorphism because isomorphisms are going to depend on the point. And when you collect, now I'm going to use a kind of my Riemann surface intuition. When I put this Ex together as fibers sticking at different points of the, keep in mind it's a graphic representation of a curve over a finite field, but okay. So you end up with the local system. This is a formulation of the geometric Langlands correspondence. So people were so excited. I guess when people, this was a bit before my time. But I imagine that when people, and the major figure here was Vladimir Drinfeld, who appreciated, well, Deligne first, but also Drinfeld appreciated this idea, and he applied it in the case of GL2. Now, in fact, he was trying to prove the Langlands correspondence for GL2, which is to construct Hecke eigenfunctions, right? So Hecke eigenfunctions, but in the GL2 case, on the double quotient for GL2, let's say. But what he did was more. He actually constructed Hecke eigensheaves. At the end of the day, he took the trace of the Frobenius on the Stokes and said, here's your automorphic function. But in fact, he did more. And then that gave birth, I would say. So this is 1983, the paper in American Journal of Mathematics. It's a beautiful result, a beautiful construction for GL2. Gerard Lamont was the next to sort of carry the torch. He really framed it as a geometric version of, stated it as a geometric version of the Langlands correspondence, dealing with sheaves rather than functions. So what I just explained is more or less what Lamont explained. 1986 is a paper in Duke. So, and then it kind of took off. The theory kind of took off. So the next major development was the work of Bellinson and Drinfeld in the early 90s. That one I was already a witness of. But that's where Lamont and Drinfeld and Bellinson said, okay, well, that's the formulation which we can now carry over to the case of complex numbers. Because now we're talking about sheaves. Okay, it's nice for a finite field. We can always go back. At the end of the day, if you're scared of sheaves, before you turn off the lights, you take the traces of the Frobenius and the Stokes. You got your functions, you can sleep. You can sleep well. The sheaves dissipate. But over complex numbers, we don't have the Frobenius. You cannot go this. There is no obvious way in which Grothendieck's dictionary could be applied. But we do have sheaves. And so people came up with this idea, people meaning Lamont and Bellinson and Drinfeld, that we'll just take the second formulation, that is to say, we'll look for Hecke eigensheaves on the Picard. This is a GL1 case, right? So, and then, of course, we can try to generalize to other groups on the Picard variety. So this is only over FQ. This is over FQ, the way I set it up. This, however, is both. It works both over FQ. Let's see if I have a workable. Over FQ and over C. And then the theory kind of took off, and many important results have been proved. So, for instance, for GL2, these Hecke eigen-sheaves have been constructed for all irreducible representations of the Galois group, of the Weil group, more precisely, two-dimensional analytic representations, not necessarily unramified, by the way. I am using the unramified case to set it up just for simplicity, but Drimfeld's work applied. No, sorry, I am. Drimfeld's work for the functions applies to ramified and unramified, but the shift theoretic applies to unramified. The point is that if you take other compact subgroups here, you get much more complicated moduli stacks. So in the geometric theory, we usually stick to just unramified case, although we do have many results for the ramification, tame ramification at least. And so that work was generalized later by Lamont and then Gates, Gary-Villanin, and myself for GLN. So now we actually have Hecke eigen-sheaves on Ban GLN and ramified case for every unramified rank n representation, dimension n representation of the Weil group, irreducible representation of the Weil group. So here we are, right? So this is where we are before Langlands' paper. And so Langlands, so when was it? About 10 years ago, I collaborated with Langlands and Bao-Chan Go on a project related to beyond endoscopy. And at that time, we had multiple conversations about the geometric theory. In fact, we used some of the ideas of the geometric theory in our paper. And Langlands was always sort of uneasy with this formulation. It's like, why are you doing sheaves? Why are you not doing functions? I want a theory with functions. And so there we go, right? So that he wants to construct, nonetheless, putting all of these concerns aside, I want to have Hecke eigenfunctions, 4 curves over the complex field. So let's see what can be done, right? Let's see if there is a theory, an analytic theory. Of automorphic functions. For curves over complex field. And that's that's a question he asks in his preprint, and he makes some proposals and some calculations in support of those proposals. Now, since time is short, I will leave the details for the you can read the details of sort of my take on it in this manuscript, in these notes, which I posted on this web page. But I would like to make a few comments. And so, my general feeling is that you first have to understand the abelian case. So, right? So GL1. So let's start with GL1. And for GL1, indeed, the question has a very good answer, a very nice answer. Quite elementary. I'm actually surprised in some sense that is maybe some of you know it, and maybe it has been done before. So what is going on for take GL1? So I already explained that. So you have a curve over C. So you have the band GLN for all intents and purposes for us. Band GL1 is going to be just a Picard variety. More precisely, the actual band G is a quotient of, as algebraic geometers will tell you, it's a quotient of this variety by the trivial action of the multiplicative group. But OK, let's just stick with the fine moduli space, which is the Picard variety. So it's more or less, let's just say more or less. Now, it is a disjoint union of, as I already mentioned, of connected components which correspond to bundles of different degrees. And we would like to define Hecke operators on functions. In fact, we can take L2 functions. There is a standard measure that we have it's a Picard variety is basically a complex torus, so it has a very canonical measure of integration, so we can define the L2 space. So we're going to do the L2 space. Now, there is a subtle point, which is that it is a disjoint union of connect components. So in fact, the Hecke, for instance, Hecke eigenfunctions, the Hecke eigenfunction is going to be in the product of the L2 spaces of those components. Not the direct sum, but the product. But it's not a big deal. In fact, if each eigenfunction of the Hecke operator is uniquely determined by its restriction to one of the components, so which is a torus. So we're really talking about L2 of a torus, of a complex torus. So let's be a little bit more precise. What are the Hecke operators? They're very simple operations on line bundles, which have been known now forever, of course. So you have, let's call it, so let P be a point of X. You have a map from peak D of X, line bundles of degree D, to line bundles of degree D plus 1. Line bundle L goes to L of P. A line bundle whose sections are on the Zariski open subset are the sections of L which are allowed to have a pole of order 1 at P. This is a standard operation. And we define HP is the operator which acts on functions as a pullback according to this map. This is a Hecke operator. Hecke operator assigned to the point P. And assigned to a point P. So they all commute, commuting Hecke operators. And so we can ask what are their eigenfunctions. Now, as I already alluded to this fact that actually it makes sense to restrict to one component. So the eigenfunctions of HP on the entire Picard variety with all these infinitely many components are in one-to-one correspondence with eigenfunctions on just one component. Let's say peak 0 of X. But eigenfunctions of the operators, you know what we can do? We can apply HP and then apply HP 0 inverse. These maps are invertible, obviously, because you have a map also from L to, so this would be T P inverse, L minus P. And we can take the HP followed by HP 0 inverse for some fixed point. Let's fix a reference point. It's convenient to choose one, a P0 on X. Then we have a family of operators where you go from peak 0 by HP. You go to peak 1, but then you come back by one and the same HP 0 inverse. So you get these operators now acting on functions on peak 0, and this is more manageable now. So in fact, we can just take the L2 space of this peak 0 and ask, what are the Hecke eigenfunctions? And it has a very nice answer, actually. The question has a very nice answer. What you do with it is kind of another point. But at least I can give you the answer. And so the answer in general is written for an arbitrary curve in these notes which are available here. Let's look at the case of an elliptic curve. Just to give you an idea, it's already a good case. In fact, Langlands mostly considers elliptic curves in his preprint. Let's say the X is an elliptic curve, and I even would go one more, and I would actually take X to be so elliptic curve E tau. I would actually take E with parameter I. So it's just C divided by Z plus Z times I. Since my time is very short, I just want to give you an idea to see that it's just basic harmonic analysis on a torus. It's nothing more. But it's nice because you cast harmonic analysis on a torus now in the framework of the Langlands program of the would-be analytic theory of automorphic functions. So this is kind of good news The abelian case really is a good news here. You have, let's say, we have z, and you have x plus iy. So what is it? It's just the product of two circles, right? So we have standard harmonics, the Fourier harmonics, which are, I should say, I'm going to, why elliptic curve? Because then I'm going to identify peak 0 of x with x itself. So each point will just go to the line bundle OX of P minus P0. This is where this P0 also comes handy. So there are standard Fourier harmonics. Therefore, I don't have to deal with peak 0. I just do deal with x itself, with the elliptic curve itself. And now my curve is the simplest one, or one of the simplest ones. It's c divided by z plus zi. So it's a product of two circles. What are the harmonics? E to the 2 pi I mx plus 2 pi I n y, right? Where m and n are the integers. And guess what? They are actually eigenfunctions of the Hecke operators. Why? Because what is the Hecke operator? It's just a shift. It's just a shift. So if you have a point P, which has coordinates xp and yp, real and imaginary coordinates, components xp and yp, then under this identification, hp, let me call this operator hp with the left index p0. This is the notation I use in my notes. Times this function, obviously, is e to the 2 pi I m xp plus 2 pi I n yp. That's the eigenvalue, right? Let's call this function fmn. So then I just write it like this. Fmn. You see? So the operator, I didn't write the formula for it. Hp p0 f of z is f of z plus p. You just shift x by xp and y by yp, so of course you get this. This is kind of standard harmonic analysis on a circle. Well, it's two circles. It's a product of two circles, but otherwise it's basic harmonic analysis on a circle. So you got here your eigenvalues, you see. So that means that actually there exists, for GL1, there exists a theory of automorphic functions. This is what Langlands, in the preprint, he strongly, how should I say, he makes a thesis that there exists a rich theory of automorphic functions. And he tries to build it, he tries to construct it, mostly for GL2 and elliptic curves. Now here we start with GL1 and an elliptic curve, and we see that, yes, he's right. He's right. We don't know what to do, what to make of it, what it's good for, but there are bona fide, legitimate eigenfunctions of the Hecke operators. What about other groups? So I'm going to be saved by the bell. So, luckily, I have this. By the way, just so you know, you see, this is his manuscript. Yeah, just so you know, I worked on it very hard. So it's been quite a journey, I have to say. Last few months, it's almost like, oops, I haven't been in this since I was a graduate student, So it's kind of going back to the roots, So it's been a fascinating kind of down the rabbit hole, kind of a trip down the rabbit hole. I try to present what I understand at the moment in these notes. So let me say this, just in closing. For GL1, the special thing about Hecke operators is that they correspond to pullbacks of functions under a very natural one-to-one map. And therefore, there's no integration. There's no integration involved. But we know very well that in the classical setting, when you have Hecke operators for curves over a finite field, for function fields, or for number fields for that matter, they are very similar. already for GL2, the first Hecke operator involves integration over what is actually the set of points of a projective line of P1. If your curve is over a finite field, FQ, it's going to be summation over Q plus 1 points. That Q might change from a point to point. It will be actually the order of the residue field of a point. So it will be some Qx plus 1, where Qx is a power of Q, the original number of points of the ground field. But if you are over complex numbers, you're going to have to integrate over the complex projective line. And as far as so in my opinion, there is no way to escape it. You have to integrate over complex varieties. You have to put a measure of integration. And that's where it gets complicated. So I have looked at different options, how to define. So Langlands does not address the question of general definition of the measure. I tried to see, and so it led me to very interesting conversations with experts in motivic integration, with experts in groups over, including Julia Gordon, who's here, and David Kashdan. Also experts in groups over what's called two-dimensional local fields. Because you see, now we have to deal, whereas in the classical setting, we have to deal with G over Laurent power series over FQ, right? And that's a locally compact group. So you have a canonical invariant Haar measure on it. But now, if we really want to have a completely analogous theory, we have to deal with G over C of T. And that's not locally compact. So there's no Haar measure on it. In fact, C of T, Laurent power series over C, is more like double Laurent power series over a finite field. And actually, there have been some interesting works on trying to, I don't have much time to discuss, but that almost nobody looked at this. But I talked to people, to experts in measure theory, Ivan Fisenko and his students, his student Raven Waller. And I read works by Waller and Morris as well. Matthew Morrow. I don't see how to use those methods to get some integration theory. So I was kind of stuck for a while. And so it may well be that there is a way to define the Hecke operators. At the moment, I don't see. However, in the course of trying to find Hecke operators, in discussions with David Kashdan, we actually saw another option, another possibility. On band G, we have global commuting differential operators. Global commuting differential operators, which actually were used by Bellinson and Drinfeld to construct those Hecke eigen-sheaves for crossover over complex field. So why not use those commuting differential operators and set up a spectral problem for them rather than the Hecke operators, whose definition appears to be incredibly difficult. And so we try to do that. I present some results of my ongoing joint project with David Kashdan. Also, I should mention that Jörg Teschner considered the paper a year ago, the case of SL2, of how this should work. There is a rich, all I can say, since I'm out of time, is that there is a rich, as Langlands expected, there is indeed a rich analytic theory of automorphic forms for band G. But it's not what you might think it is. So that's sort of the summary of my talk in one line. And it's kind of clear, in retrospect, it's kind of clear because I give a kind of explain in the notes, in these notes, I explain a kind of a toy model. A toy model would be that you take, for example, instead of spherical Hecke algebra, you take a Hecke algebra, which is the finite dimensional Hecke algebra, which is a deformation of the group ring of the Weil group. For example, even for SL2. So you have you can think of, so B is a Borel subgroup in G over finite field. right? And so you can look at the Hecke algebra. HQ of G is B by invariant functions on the finite set G of FQ. This is a Hecke algebra, right? So you can think of it as B invariant functions on G of FQ divided by B of FQ. Obviously, there's parallels between that and this case. You would, instead of the flag variety G mod B, you would have affine Grassmannian and so on. Instead of the group B, you will have G of O, the Taylor series, etc. So what should we do? How do we build an analog of this theory when we go from FQ to C? So there are two ways. One is categorical. Instead of considering invariant functions on this quotient, we consider B equivariant sheaves. So one, B equivariant sheaves on G mod B. Two, and that's a very rich theory. It has many applications to representation theory, to various Harish-Chandra categories, etc. It's a very, very, we get the action of this category on the categories, on various categories of Harish-Chandra modules. So it's a very rich theory. But we don't have don't take functions. We take sheaves. But we can also take functions. You see, you can also take, let's say, L2 functions on P1. For instance, G equal SL2 is going to be just G mod B is just P1. You take P1. L2 function P1. But on P1, you don't consider convolution algebra because the integrals will not give you a good thing because there are infinitely many points. So you basically, I explain it in the notes. If you try to make sense of B invariant convolution product of B invariant functions here, you basically forced to say that the measure of a point is non-zero. But then there are infinitely many points, so the integrals are going to diverge. But there is another option. There is Laplace operator, you see. And so why not take Laplace operator? You have the Laplace operator, and it almost has a simple spectrum, L times L plus 1. Because, in fact, under the action of the compact, you can also write it as SU2 modulo U1. So you actually have an action of SU2, and from Peter Weil theorem, you know that it's a model, it's a direct sum of reducible representations. On each of them, the Laplacian is going to act as a Casimir. And if you want, take the right action of U1 to really get simple spectrum. So you have two differential operators of second order and first order, which completely separate the spherical harmonics. That's more in line with what we are supposed to have for complex, in the complex case. And the remarkable fact is that this exists for Bun-G. There are commuting differential operators on Bun-G, just like there is which come from the center of the Kac-Moody algebra. Just like there are commuting differential operators on the flag variety coming from the center. And my sense is that one gets a very rich, and so with Kazhdan we have some, Teschner has obtained some partial results, with Kazhdan we have obtained some results, some of it is explained in the notes. But my current view is that that leads to a very, to a rich, fascinating theory, analytic theory of automorphic functions for complex curves. Thank you very much. Of course.
That paper wanted to introduce integral operator, which demanded a knowledge of Bun-G. Knowledge of Bun-G, we have very few groups. We have basically for elliptic curves and maybe geometry. And
It's not neglected in my notes. It's not neglected in my notes.
Okay, good. Good. So,
I spent a few months of my life, trying to understand, sir, with all due respect.
I hope if that's the case, I hope people read your notes. But if it's not in your notes, the essence is, I think, of the problem is to understand Langlands in general and to introduce integral operators. But I may be wrong. And if that was the first purpose of my paper, and there was a second result that I wasn't aware until very recently. And I think it's a significant thing, but it's not really relevant to what it's an incidental consequence. And that is that the category of automorphic forms over in this geometric situation seems to be defined by groups, whereas in the strictly arithmetic situation, you seem to see this Finoutian category. So the result to which my conclusions are pointing is this somewhat unclear statement that one G is defined as a Finoutian category by a group and its representation. Whether that's true in general or not is something else. In any case, my impulse is certainly different from that you presented today, I think.
Right. So that's what I tried to address. Your emphasis was on the defining Hecke operators, so attempting to define Hecke operators, acting on certain space of functions in the case of elliptic curve and GL2, right?
Right.
Now, I have looked at first of all, for GL1, Hecke operators are well defined, as I explained, because they do not involve integration. For non-abelian groups, as I argue in these notes, Hecke operators involve integration, and therefore, in my opinion, they're problematic. Let's just say problematic. So I do not see how to define them. I do not see how to make them well defined in this context. However, that's the bad news, so to speak, for me. The good news for me is that we don't have to. It's just like in the case of P1. One could try to define a convolution product of invariant functions. It's problematic. But instead, well, in this case, the Hecke algebra is not commutative, so it's not precise analogy, but you see, it's very similar. But there are other means, you see. So we know that when we are in an Archimedean context, there are tools available to us which are not available to us in a finite field. Differential operators. Sure. Well, in my opinion, one works and one doesn't. So that's our hand is forced.
In any case, you cannot assert. I was hoping you would assert that I read this paper and it is in fact valid. But you can't say that.
Sir, I'm a witness. Tradition of mathematics going back to Pythagoras and so on is that it's decided by truth, not by authority. So I'm bound by my vow. So, but it is my personal opinion.
You're bound by the clock.
And the clock as well.
We decided, in view of everything, we decided to postpone the next talk till 2 o'clock, and the talk after that postponed also 1/2 hour. So the next lecture is 2 o'clock, and the one after that I forget what 3:30.